what we want to do is to begin our discussion of the second law of thermodynamics, which involves entropy, which we discussed in class. So entropy, as you recall, is nothing more than a measure of the disorder in a particular system or as a result of a chemical reaction. So the second law of thermodynamics states that for a particular process to be spontaneous, and this is where we bring entropy back into spontaneity, as we were talking about in class. It says that the delta S of the universe, which is the sum of the delta S of the system, which is normally delta S of the reaction that we're looking at, plus the delta S of the surroundings, has to be greater than 0. And you'll remember here from your prior thermodynamics that anytime we talk about any quantity involving the universe, that is going to be considered that quantity for the system plus that quantity for the surroundings. Recall that system plus surroundings together makes the universe. So again, what we have to show is that for a reaction or a process to be spontaneous, we have to see a positive delta S of the universe. Right? That is our requirement for spontaneity. So in order to do this, what we see that we have to be able to do is we have to have a means of calculating the entropy change of the system, but we also have to have a means of calculating the entropy change associated with the surroundings. So how do we do that? So if we focus on the system part here, what we find is that we're going to use this reaction, or rather this equation here, to define the standard state delta S of the system. So notice here that system and reaction are one and the same, because we're focusing typically on a chemical process or a chemical reaction here. Now, we're also going to use standard state values because these are tabulated values. So normally when we do these kinds of calculations, we will use standard state calculations at a particular temperature. So those will either be given to you or you can find them in the tables in the textbook. All right, so because the delta S here for a particular reaction is a state function and therefore pathway independent, we can use this good old equation here, just like we did in the case of enthalpy. So what we see here is that if we have a series of standard state entropies for products and reactants that we can look up in tables, we can calculate a delta S standard state of reaction. It's just the summation of the delta S's for my product standard state, taking into account my stoichiometric coefficients, and we subtract from that the summation of the delta S's of the reactants, also accounting for stoichiometric coefficients. And we'll look at an example of this in just a moment. So this is how we can actually focus in and calculate the entropy change associated with a chemical reaction. Now, what about the delta S of the surroundings? That's the other piece of the puzzle that we need. So in this case, we're going to use this particular equation. It says here that the delta S of the surroundings is going to be the negative of the delta H standard state of the system. Okay, again, we're focusing on the reaction here, divided by the temperature at which that particular reaction occurs. All right? So this kind of makes sense when we think about it. If, for example, we assume an exothermic delta H, that means the heat is being given off. Now, what effect is that going to have on the entropy of the surroundings? So if I think about a reaction that's giving off heat, and I think about the surroundings as being, for example, air molecules and such around that, what's going to happen here is as those air molecules absorb that heat, they're going to move faster. And as a result, they're going to become more disordered. So what I would expect to see for an exothermic process is going to be an increase in the overall entropy of the surroundings. So that's the other piece of the puzzle that I need. So let's take a look at an example of how we can use these two calculations to come up with natural prediction of a process to see whether or not it will be spontaneous at a given temperature or not. All right, so let's take a look at a problem where we actually get to calculate or predict reaction spontaneity at a particular temperature. So we're asked here to predict whether this reaction is written as spontaneous or non-spontaneous at a given temperature of 298 Kelvin. I chose this temperature because it's room temperature and our thermodynamic data in our tables are tabulated at that temperature, so that's a good place to work. All right, so here's the reaction. It's carbon monoxide gas reacting with hydrogen gas to give us methyl alcohol, or CH3OH, in the liquid form. And it's important here to take a look at chemical states, because when we look up our thermodynamic parameters, these will be state dependent. So I'm going to be very careful to list states so that when we go to the thermodynamic tables, we know exactly which numbers to choose. Now, these are numbers that I looked up in a thermodynamic table for these particular specimens. So for carbon monoxide, for example, the standard entropy at 298 is 197.5, and that's in terms of joules per mole Kelvin for all of my standard entropies. Likewise, if I look up a delta H standard state, that's going to be minus 110.5 for carbon monoxide in the gaseous form in kilojoules per mole of reaction. All right, so again, pay attention to those units. Now, again, those are numbers that I go and look up in the thermodynamic tables. Now that I have them, I can use them. Now remember, one of the things that we have to do here is we have to calculate a delta S for my system, or for my reaction. So I can use my equation that I gave you before to do that, where we're looking at the summation of n times the delta S of the products minus the summation of n times the delta S standard state of the reactants, where the n's here represent stoichiometric coefficients in my balanced reaction equation. So just to review how to do this kind of calculation, let's take our numbers for our standard state entropies that we have over here on the opposing board, and let's place them in here, making sure that we put our stoichiometric coefficients out front. All right, so starting out with the products, I have 1 mole in my stoichiometric reaction here, 1 mole of the CH3OH times the standard entropy here. All right, that's the only product I've got, so I'm going to subtract from that now the standard entropies for my 2 reactants. Again, weighted according to their stoichiometric coefficients. So you see here that I have 1 mole of the carbon monoxide times its standard entropy. And I'm going to add to that my 2 moles from the balanced chemical reaction equation of hydrogen gas times its standard entropy of reaction. All right? So when I do that, what I'm going to get is a value of minus 332 joules per mole Kelvin. Now be careful here, because you might say, well, moles will cancel top and bottom here, and technically they do. But I'm going to leave the moles down here in the bottom, because whenever we look at these delta S values for a given reaction, these are understood to be joules per Kelvin per mole of reaction. So I'm going to leave the moles in there to remind ourselves that this is per mole of reaction. Now we can do the very same thing to calculate a delta H standard state for my system or my reaction as well. So I'm just going to use the very same approach, very same equation, but now I'm going to use delta H's in place of delta S standard states. And those are those very same delta H standard states that I've got over here in the bottom on the opposing board. So you can do that calculation for practice and then verify my numbers. What I get for the delta H of my system or my reaction is minus 128.1 kilojoules per mole. Now I'm going to convert that over to joules per mole, as you're going to see in just a moment. And when I do that, I'm going to get minus 128,100 joules per mole. Again, I'm doing this so that when we actually pull everything together, the units are going to relate to one another. So now that I've got these 2 values, the delta S for my system, and I've got the delta H for my system, now I can calculate exactly what I need to calculate to determine whether or not this is going to be a spontaneous reaction or not. So that's the next step. All right, so just to remind ourselves of what we have here, we had calculated just previously a delta S, or rather a delta H standard state for the system of minus 128.1 kilojoules per mole, which I converted to joules per mole, and I got minus 128,100 joules per mole. Also, just to remind ourselves of what we got when we calculated the delta S standard state of the system from that prior calculation, that was minus 332 joules per mole Kelvin. So these are the numbers that we've calculated up to this point. So what do we now want to do with them? Well, the next step is that I need to calculate a delta S of surroundings here. And remember, I have an equation for that. The equation is a negative delta H standard state for my system divided by the temperature at which I'm working, which in this case is 298 Kelvin. So I'm going to take my delta H standard state from the other side of the board that I calculated in joules per mole, and I'm going to stick it here for my delta H standard state of my system. Divide that by 298 Kelvin, I get 430 joules per mole Kelvin. All right, so again, keep in mind this is per mole of reaction. Now, what's my requirement for spontaneity? Well, my requirement for spontaneity is that the delta S of the universe has to equal to the delta S standard state of the system plus the delta S standard state of the surroundings, and those things together have to be greater than 0 for a reaction to be spontaneous. So if I put the correct numbers in here and notice that the units do match up and I add them together, I end up getting a positive 98 joules per mole Kelvin. We see that that's a positive value. It's greater than 0. So what that tells me is that this particular reaction, as it's written at 298 Kelvin, is going to be a spontaneous reaction. So the take-home message here again is that I cannot say anything about reaction spontaneity by looking at enthalpy alone, nor can I say anything about reaction spontaneity by just looking at the delta S of the system alone. I have to take into account the delta S of the system and also the delta S of the surroundings together to determine whether or not a reaction will be spontaneous or not as written.